we continue the nucleon scattering. In order to study the nuclear force, first we have discussed the neutron problem, and later we discussed the nucleon scattering. And in both these cases, we have assumed that the potential, that means due to the force between the nucleons, the potential is a square well potential. And in order to get a more depth into the studies, we used the partial wave analysis technique. That means you are assumed that uh, when energy is low, the incident nucleons can be considered as waves, or more clearly, plane waves. And these plane waves can be considered as a sum of spherical waves. And after scattering, the scattered waves is spherical waves. And in last class, we have derived this equation. Psi scattered is a by 2ik, where a is the amplitude, to e raised to 2I delta 0 minus 1 e raised to I kr by r. And this last class, this delta 0 means it is the phase shift for L is equal to 0. That means we are assuming that the orbital angular momentum is 0. So for L is equal to 0, you can take it as delta 0. And we have already mentioned this equation also. That means using your equation 12 in last class. The expression for J scattered means it is the current density of the scattered particles. It is given by h cross by 2mi psi star di psi by di r minus di psi star by di r psi. And to solve this, you have this psi, and you can do psi by psi star, substitute here. And to find psi star, it is the complex conjugate, so you have to change this I to minus I. That is not u. So you can make this psi. This here, this psi stands for psi scattered, and psi star means psi scattered star. So you find psi star and also find di psi star by di r. You can do that, and on solving this, you will be getting this equation: h cross a square by m k r square sine square delta 0. And the incident current or incident current density you can write as J incident is equal to h cross k a square by m. This is also a non-equation. And from these equations, our equation for the differential cross section is d sigma by d omega as r square into J scattered by J incident. Substituting for J scattered and J incident in this equations, you will be getting d sigma by d omega. That means the differential cross section as sine square delta 0 by k. In general, d sigma by d omega varies with the direction over the surface of the sphere. In the spherical case of L is equal to 0 scattering, d sigma by d omega is constant, and the total cross section sigma is, sigma you can write as integral d sigma by d omega into d omega. And this d sigma by d omega we have written as sine square delta 0 by k square. And we have mentioned that for a spherical surface, this d sigma by d omega or this term sine square delta 0 by k square is a constant. So it can be taken outside the integral sign. And you have the remaining is integral d sigma. Integral d sigma means it is the integral of the solid angle, and the total solid angle is 4 pi. So this becomes sigma equal to 4 pi sine square delta 0 by k square. The L is equal to 0 phase shift. Delta 0 is directly related to the probability for scattering to occur. That means there is a direct relation between your delta 0, that means the phase shift, and your total cross section. Total cross section means it is the probability for occurring of scattering. That is, we can evaluate delta 0 from our simple square well model. We have already discussed it, and compare with the experimental cross section. So, to check the validity of the things we have done, what we will do is, you can measure the cross section using some techniques. And here also, by a knowledge of this delta 0, our discussed equations, we will be trying to calculate the cross section. And this will give an idea regarding the things we have done. And in order to understand the data taken from the low energy neutron proton scattering, we may return to the analysis of equation number 8. And this was our equation number 8 by putting in proper values for all related quantities. This was our equation. K2 cot K2R plus delta is equal to K1 cot K1R. This is the equation with our nucleon scattering, and this delta was the phase shift, and we have mentioned that this delta is positive for attractive potential, and it is negative for repulsive potential, and it is equal to 0 for free particle. And this K1 is the K1 is within the square well, and K2 is outside the square well. And we have the expressions for K1 and K2. And now we assume that when the incident energy is small, so nearly of the order of less than 10 kilo electron volt, etc., and we have this V0 is equal to 35 MeV. This is our analysis of neutron bound state. So we have the equation that for a deuteron, your K1 is equal to root of 2m into minus b plus V0 or V0 minus b by h cross square. And there the energy of deuteron was taken as its binding energy. And in scattering, that energy is taken as the energy of the incident nucleons. So if you substitute this V0 that we know from the deuteron problem, you will be getting the value of K1 as 0.92 femtometer inverse, or 1 by femtometer. And K2 can be, in place of that B, you have E, that will be very small, 0.16. And this is outside the well, this is inside the well. And this equation, K2 cot K2R plus delta is equal to K1 cot K1R. that K1 cot R, this one, K1 cot K1 R, this value you are taking as minus alpha. That means K2 cot of K2R plus delta 0 equal to alpha. And this substitution is for a comparison between the deuteron. And for deuteron, we have shown that the value of R is 2.1 femtometer. So now we are taking it as 2 femtometer. And this K2, the value is very small. So this is much less than 1. So you are now neglecting this. And we have K2 cot delta 0 is equal to minus alpha. Or cot delta 0 you can write as minus of alpha by K2. And now this relationship K2 cot delta 0 is equal to minus alpha is analogous in the form of the equation K1 cot K1R is equal to minus K2, which describes the binding energy of deuteron in terms of same rectangular square well potential. And this was our equation for deuteron. And after a substitution, this is our equation for scattering. It is here in place of K1 we have K2, and in place of this K2 we have alpha, both with the minus sign. For that is why we have taken this as minus alpha. So K2 cot delta 0 is equal to minus delta, and K1 cot K1R is equal to minus K2. So the two relations. And one more thing is to mention is, in the wave equation, we haven't used the letters K1 or K2. It is just K, e raised to minus IKR as well as e raised to IK. And that K, as you know, it is your 2 pi lambda. And its dimension is reciprocal of length. So there, this K1, K2 or K, they are similar quantities. And for low energy nucleons, that means energy much less than V0, we may assume that the wave function inside the well is nearly the same for the deuteron. For deuteron, you have B much less than V0, and the nucleon scattering system. That means wave function for nucleon scattering system and deuteron are same. That is why you can nearly take as the C is equal to B. So you have, from this comparison, this K2 must be, this is a similar equation. In place of cot K1R, you have cot delta 0 minus alpha minus K2. Okay. So for a similarity, you can say that this K1 and K2. And for approximation, we can write the first one is E is equal to B, that we have written. And this K2 is for scattering. K2 for scattering is equal to K1 deuteron. Comparison of this equation. And we have K2 written as 2m by h cross square. This expression for K1 is 2m by h cross square minus B plus V0. And for, since this E is equal to B, you can write it as 2m by h cross square E plus V0. And for scattering wave function, we can take K as K2. For scattering, we have only one wave function K. So, no K1 and K2, only K is there. And for most of the time in scattering, the K is just at the K1 is only at the time of the scattering. So for the scattered wave, that means it is after scattering, that means outside the potential wave. So outside the potential, you are taking the value as K2. So for the wave, you can take K as K2 and this V0 equal to 0. There is no interaction, so V0 is 0. So your equation becomes, this K2 becomes K. K is equal to root of 2me by h cross square. And this alpha is for scattering and this K2 is for deuteron. So alpha for scattering is equivalent to K2 for deuteron. That is alpha is equal to, our expression for alpha is root of 2mb by h cross square. We are simply taking that equation and we are not substituting this b with e because we need two equations. And we have the equation for total cross section as 4 pi by k square into sine square delta 0. Here, the last case we have mentioned this as sigma, total cross section. And now, for L is equal to 0, you are replacing it with a sigma 0. So, sigma 0 is equal to 4 pi by k square sine square delta 0. And now this can be written as sine is 1 by cosec. So, it is 1 by cosecant square delta 0. And 1 by cosecant square delta 0 can be written as 1 plus cot square delta 0 because we have an expression for cot. And this cot delta 0 is minus alpha by k2. And since k2 is equal to k, you can replace this as alpha by k. So cot delta 0 is equal to minus alpha by k. Now you can substitute for cot delta 0 as minus alpha by k. So that is sigma 0 is 4 pi by k square 1 by 1 plus minus term on squaring becoming plus alpha square by k square, or it is k square by k square plus alpha square. This k cancels. So 4 pi by k square plus alpha square. And now we can substitute for k and alpha. K as 2me by h cross square and alpha as 2mb by h cross square. Or you will be getting sigma 0 as 2 pi h cross square m into e plus b. So now you have an expression for scattering cross section in terms of energy of incident nucleons and also the binding energy of deuteron. And this relation was derived by E.P. Winger, and it agrees with the experimental results at high energies but fails at low energies. So at energy somewhat high, you can see that as energy increases, scattering cross section decreases. That is possible. And substituting of B and E in equation 22 gives sigma 0 as, because we have the value of E as some 10 kilo electron volts and B, as you know, it is 2.225 MeV. We will be getting sigma 0 as 2.3 barns. Barn means it is the unit for area, and 1 barn is equal to 10 raised to minus 28 square meters, which is in violent disagreement with the measured value of sigma 0 equal to 20.4 barns. This is, the measured value is 20, but here we are getting it as 2.3. And figure shows the experimental cross sections for scattering of neutrons by protons. You can see that for up to a energy, that means for low energy, more than 10 raised to 4 electron volts, it is nearly constant, and then only it decreases. And for low energy, that value is 20.4 or 20.36 barns. In that place, we are getting it as 2. But you can see that our equation, thus it is divided by E plus B. So when E increases, total cross section decreases. So it is true when energy is high. So at a high energy range, this equation is applicable. So in this figure, the experimental cross-sections for scattering of nucleons by protons is indeed constant at a low energy and decreases with the E at a large energy, as our equation number 22 predicts. However, the low energy cross-section 20.4 bonds is not in agreement with our calculated value of 2 to 3 bonds. This has to do with the spin-dependent characteristics in nucleon-nucleon interaction. So now we will be trying to, that means your neutron and proton has spins. So if their spin can be either parallel or anti-parallel. So we may assume that the interaction may depend on the orientation of spin. That means when you have parallel interaction, maybe with the stronger or less than the interaction when they are anti-parallel. So we will be considering that spin dependent, and we will try to correct our expression. And if that is done, what will be the result that we can do in the next class? So what we have done is we discussed the neutron problem, and we got some fundamental concepts. And by studying the nucleon problem, we have some comparison, and we have some conclusions which is almost true, and we will be trying to correct our assumptions to get more accurate results, and those things we can do in the next class. And that's all. Thank you.